Don't talk. What are you talking about?
We're
I
good?
think that's more
Yep,
than
I don't
Okay.
think you started it.
All right.
It has a red
So
dot.
let's talk about question number 6 in the back. This is somewhat relevant to the quiz that you're going to have today. Okay? So here's this rubber stopper, and you're going to swing it around like this. So imagine I happen to have a rubber stopper on a string. Okay? So I'm going to swing this thing around, right? And so we're going to know the radius. We got that. And you're at 1.8 meters above the ground, which would be about like this. Okay? So I'm swinging it around like this. Boom. I let go of it. So because I'm swinging in a horizontal plane, what's my initial vertical velocity? 0. Okay? So this is just like throwing this thing off of a cliff. Okay? So that's one of the two types of problems you're going to have. So that initial velocity is going to equal to 0. So since the initial velocity is equal to 0, what are the only two things that determine how long that rubber stopper is in the air? Gravitational acceleration and
Distance.
how far it falls, right? But that's your vertical distance, because what happens in the y stays in the y, what happens in the x stays in the x. So you're told that it's 1.8 meters above the ground. So whether I just drop that rubber stopper and have it fall straight down, or if I throw it out, doesn't make any difference. The gravity mafia could care less about Vx because it doesn't have any influence on it. The gravity mafia only controls what's happening vertically. So if I throw that out, or if I drop it, it's going to take the same amount of time. And you can go, oh, distance equals 1/2 at squared plus v naught time. So don't confuse that Vx as your initial velocity, because that acceleration is only going to affect your vertical. So, oh, that part goes away, 2d over a, the square root of that, boom, there's my time, okay? So your time should be about 0.6 seconds, okay? Roughly, should be about 0.6 seconds. Now, you know it's going to travel 4.4 meters. So imagine that I'm here, I'm swinging this thing around, I let go of it, we measure it, it lands 4.4 meters away. So that's going to be your range. And then you know range equals Vx time, okay? So now you know how long it's in the air, you know how far it went, so then you can get that Vx. Your Vx should be around 7 meters per second. And then you can find the centripetal force. Because why do we have to continuously exert a force to make this rubber stopper move in a circle? Why does there always have to be a force to make it move in a circle? Because if I don't have it, what does it do? It goes off in a straight line because Mother Nature doesn't like circles. Okay? Mother Nature likes straight lines. Okay? So to make it go in a circle, you always have to provide a force because Mother Nature doesn't like circles. Mother Nature likes straight lines because that's easier. Okay? So Mother Nature goes, you want a circle? Hey, cool. You provide a force. You don't provide a force? Whoop, I'm out. Okay? So your overall answer on C, on number 6, should be something close to your current age. Okay? Something close to that current age. So, when I ask you about the direction of a centripetal force, you need 2 parts to your answer, okay? Number 1, when that rubber stopper is going around, this is going to be important in terms of the lab that we're going to do today. That force is going to be acting inward, okay? So either I'm holding onto the string or I'm using a weight or something. Something is providing an inward force, and that force is at a right angle to the motion of the stopper. Okay, so it's always inward and at a right angle to that instantaneous velocity vector, because that's the direction that it always wants to go. Okay, so there's 2 parts, inward at a right angle. And that's why I've got on that front page on J, Excuse me, an I, when it says, what's the direction of the force? And I said more than one word answer, and I said make it right. That's where you're gonna say, oh, it's acting inward and at a right angle to the velocity vector, okay? That's what I meant by that, okay? On that first problem, both of those coefficients of friction on J and K should be really small numbers, okay? Like really small numbers. So, and that's cool, because that's like the minimum coefficient of friction. So if your coefficient of friction is more than that, you're gonna make the turn, okay? And your typical coefficient of friction between shoes and ground is about 0.8. And so since that coefficient of friction is much bigger than that, that's what allows you to make that turn. And let's just say hypothetically, on J, let's say you have this as your coefficient of friction. Let's just say you have that written down. How happy am I going to be? I'm not. I'm going to blow a gasket, okay? How many significant digits does that have? One. In great pain, when I was giving you these numbers, I gave you 3 significant digits, okay? Now, if that's your answer, which it shouldn't be, don't come in there and go, oh, just put zeros on, okay? No, don't do that, because that answer is not exactly 0.004, okay? Do not just chuck zeros on the end of it and go, oh, that will appease Burkamp. No, that will make me even more angry, okay? So do not have that as your answer to J. Okay, anything you want me to go over on that centripetal motion assignment? Your answer on that velocity on number 3 should be between 10 and 15 meters per second. And your force on number 4 should be an ish around 500. Maggie?
You go over I on the front.
I on the front? What's the direction of the force?
The bottom, or L.
Oh, okay. I was going to say, what kind of words?
No,
Okay. All right. So here's the deal. So you're asking about what's going to happen to the amount of static friction. So when you have centripetal force, you'll notice one thing. When you look at the 4 fundamental forces, gravity, electromagnetic, strong nuclear weakness, notice that the centripetal force is not one of the 4 fundamental forces, okay? Centripetal force only exists because of something else, because of gravity, because of a string, because of friction, okay? So let's say this thing is spinning, and here's Albert Einstein, okay? And Al is going around like this, okay? So when you look at how you're going to calculate that centripetal force, that's mass 4 pi squared r over t squared, okay? That's one I want to use for this one. So as Al walks towards the outside, what happens to his mass? Stays the same. As Al walks towards the outside, what happens to the amount of time it takes for Al to make one revolution? Stays the same. Okay? So as Al walks towards the outside, what happens to the radius? It increases, right? So as he goes to the outside, he needs more and more centripetal force to allow him to travel in that circle. Okay? So what that means is that if we had a rope tied to Al and we were swinging Al around, there would be more and more tension on that rope as Al got farther to the outside. If we were using the Acme dehydrated gravitational hole, that gravity would have to provide more force as he went towards the outside. But since it's friction, we just need more and more friction. But friction can only provide so much force, and that's why that nickel yesterday spun off first, because it needed more force than what friction could provide, and it goes, okay, I'm out of here. Screw it, I'm done. So, does that answer your question?
So just put it like, because of that equation,
Yeah.
well, the mass and the time stay the same.
Yeah, and then just say as the radius increases, you need more centripetal force, so you need more friction.
Okay.
Does that make sense?
Yeah.
Okay, Taylor.
So that force is acting inward
Yes.
And so force of friction is acting out?
No.
Okay, no.
No. Because if friction was acting out, friction would be pushing it. Friction is acting inward. Because friction is what's providing the centripetal force.
So no force is acting out.
Outward. There is absolutely no force acting outward. None. Zero. Zip. Nothing. Nothing. When you're dealing with centripetal motion, there is, and this is why the Greek word centripetal means inward seeking. Okay? So all forces, when you're talking, whether it's gravity, whatever, will always act inward. Okay? Now, centrifugal is what Jack would experience. So when Jack, we talked about yesterday, Jack was driving his Jeep, and Jack takes that hard right-hand turn, and he feels like he's being pushed against the car door. Okay? That's centrifugal, which means outward seeking. But that's just what Jack is. Jack thinks he's being pushed to the outside, but there's no magical force pushing them. He just has inertia, which is not a force, because Jack just wants to move in a straight line, and the door says, no, can't go there. Okay, I'm going to keep you from doing that.
Okay.
Okay?
Okay, so the object is not being...
Yeah, there's
object
nothing
is
pushing
just-
it. It just wants to move in
okay.
a straight line, and the strain, gravity, with friction is just preventing it from doing that.
Okay.
So it's just like this. Okay, let me give you an example. Let's say this is volleyball. Okay, and let's say that it's rolling straight. Okay, so here's the path of the volleyball is rolling straight. And I want you to make that curve and go to the right. Which direction are you going to kick?
That way?
Yeah, you're going to kick it to the inside because the ball wants to go in a straight line.
Oh, and I'm the force.
And you're the
putting
force.
it in there. All right. That
You're
makes
the
sense.
force. Okay?
Okay. Got
Got
it.
it? Okay. All right. Anything else? If you have not handed in both that last assignment on the white sheet or that tan sheet, if you handed in that tan sheet with lab, I've graded that and I've got it back to you. But a lot of you need to hand in that white sheet and then also the green sheet on the centripetal motion stuff.
Why don't you get up and do it yourself?
Yeah. No,
About like usual.
0%. I took it off. We're gonna have a good day because I took my sweatshirt off.
Huh?
I took my sweatshirt off.
You just raised your score by at least 10%.
Okay.
Okay, so on the quiz, no, there's not a backside to it. Okay? There's 6 questions, 3 of them are multiple choice. Okay?
No, I hate multiple choice.
So, on the first one, we're just going to shoot Justin Bieber. I swear to God, that's what the problem says.
Yes, I love Justin
Bieber is
Bieber.
getting launched horizontally. Okay? On the second one, we're going to hit a golf ball. Okay? And I'm going to give you the total flight time. And I'm going to give you how far it goes. That one you work backwards. Okay? And when I say, so here's what you're going to find. So the golf ball, oddly enough, is going to take a path like this. What you want to find is the Vx, the Vy, and that initial launch velocity and that angle. So this is just like the marble lab that you all did. Okay? I've given you the data, and you work backwards to find all of those. Okay? On number 6, I'm going to give you the information about the launch. Okay? So the angle is 38 degrees, and it's launched at 30 meters per second. Okay? So you're going to find out all this information. And then it's going to be a similar situation. There is a wall out here, and it's 6 meters tall, and it is 81 meters away. You want to figure out if the golf ball is going to clear the wall. Okay? There you go. All right, you all know the drill. 1 person per table. There we go.
Took a while.
I know.
Assuming that these numbers are right, is that the pressure line? Usually that's the pressure view line. It's not initial, it's just that hypotenuse.
Oh, well, that's what I thought at the beginning when I was.
It's just the reverse of what we did here.
But I thought, when we find those, we just don't
now when you're finding these and you're working backwards to find it, you're just reversing the process. On that one, I gave you the hypotenuse and you found the sides. On this one, I'm gonna find the sides and then the hypotenuse.
So if like this comes from, I don't need that anymore.
No,
Okay.
no.
Okay.
Yeah.
Thanks.
So that's how long it's gonna take. So that's the everything's right. Maybe we're missing something on the You have everything right. Okay, he's spot on her. Other than putting that.
Do you work this weird or am I just dumb?
Huh?
Do you work this weird or am I just dumb?
Okay, there's no way I can answer that. On either side of this coin, okay? Either I'm a jerk or the other alternative isn't good.
I think
Okay.
it might be me.
So,
I don't want to turn my brain under. I need a brain break. There's nothing that's gonna save me.
Okay. I don't know what I did the first time, but it makes sense now. I don't know what it's
okay.
I can't do this.
Sorry, I'm thinking that was supposed to be.
Huh?
I'm thinking that was supposed to be.
Break. I thought I'd get a break. What?
So then,
This has been recorded this whole time.